Welcome to the third lecture in parallel programming in the summer 2024. Today we are talking a little bit about performance modeling, and this will be a little bit in two parts. Namely, the first part will be pretty simple modeling of parallel performance, in a very platonic way, with lots of assumptions, and then we go into a little bit more hardware-oriented way of modeling performance, also for single-core architectures, or independent of the parallel programming paradigm used. Okay, we start with returning to the question that last week, we've already introduced how much faster can we solve a problem with n cores compared to one core. So this is, of course, the central question, or one of the central questions that we want to address in parallel programming. Yeah, we take more cores, or more compute nodes, or more entities that do work, and how much faster will the work progress. And then you remember my question, there is a column that has to be built by bricklayers. So one bricklayer takes 1 hour. How fast will 3,600 bricklayer build this one column? And then you see you could either say there should be a second, or wait a second. That cannot be. The world is a little bit more complicated. Okay. So this kind of question is in parallel programming associated with the so-called strong scaling. So strong scaling is when we assume that we have a problem of a given problem size. So we have an amount of work that has to be done, like building one column. Yeah, and here the question is, so I could solve this problem with few resources, or with many resources, or with large resources. Yeah, but the problem will always stay the same. We are not scaling the problem size, we are only scaling the resources. This is what we mean here. So scaling resources but not the problem. Okay, in pictures, say we have an amount of work. Yeah, so this is our problem. And we have, say, a worker, so we could have one worker to do all of this, or we have the same amount of work. So now I have to guess what's the same amount of work. So we divide this between one worker and another worker, and now we go up. Yeah, you see, now I wanted to go up and not down. So like we could divide this with 4 workers, so we'll have worker, 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 and okay, I hope you get the thing. It is just, as I already said here, the constant size, constant problem size varying number of workers, and how can I get rid of this? Okay, you are right, we always have problems, workers. So, and constant, or what we mean by workers in this context is usually compute cores, yeah? Or could also be compute nodes. It doesn't really matter. So say we draw now a picture where this here is the time that we need, and here is, say, here's kind of the number of cores or workers, and say here's one worker, and now the work that would be done by one worker would, for example, look like this, and now I need a little bit some other color. Say we have this part of the work, and we have, say, that part of the work, and we say that this, okay, now I have to change it again. What am I doing? So, this part here, this light blue part, is, this is something that we call P, and it is the, okay, I write it on the, is the time of the parallelizable, ideally parallelizable code. So this is work, sorry. Yeah. You know, I'm always looking for a software that doesn't, I mean, each of them is just does something strange, right? So time, so it's, the time used for parallelizable code, and then we have the green one as this is the time of non-parallelizable code or work. Okay, maybe I should. Okay, let me do a little correction and say this is work rather than code. So give me black. So this is. So what does it mean? So your task, whatever you do, contains things that you could split up between different workers, and there are parts that you cannot split up between different workers. Yeah? And as long as you have one core, this doesn't make any difference, of course. So now suppose you get more than one core. Then what happens if you have, for example, two cores, then what happens to the perfectly parallelizable part will, of course, be that we have now only half the time that we need, because we distribute it between two different guys. So we'll assume, no, we actually have this only half the size. The non-parallelizable part, this stays the same. And now we get something else which I've not yet introduced, namely the interaction between the two. Yeah? So to speak, the communication. So I need another color which I've not yet had, so take it red. Okay, so then communication is starting is starting. Say we have here. You want light? No. Musma. Okay. Do I have to cut this out from the? No. Musma. Okay, so this we call C. Yeah, this is the communication. So this is the time for inter-process communication. So this part actually goes up when you work together. Yeah? So if you work alone, you don't need to communicate unless you're talking to yourself, which is sometimes also useful. Yeah? But this part now goes up if you have more workers, so communication goes up. So, and of course, when you scale these things up, what you will finally end up with is you go to infinitely many. So then the parallelizable part will be flat. Yeah, so there will be nothing left of these, more or less, yeah, because we divide it between a very large number of workers. Nothing has happened to the non-parallelizable part. I think I did not take the same green here. So. And the red part, well, the red part actually can grow, can in principle grow pretty large, but we assume that we don't need to take this into account. So for the guys who are a little bit have difficulties with color, I draw a black outline to this. Okay, so this is what happens. It means if you go to infinitely many workers, you don't go to zero time, obviously. Yeah, actually you can, depending on how much communication you need, actually the time that you require can increase with going higher. So it could actually going for infinity potentially it could even go, infinitely large because you have infinite much amount of communication. Okay, because the problem size is limited, communication should also be limited. Yeah, so say this. So then, in order to take this a little bit more into numbers, we say that okay, I mean, so if numbers of cores goes up, then the parallel part goes down, the serial part stays the same, and the communication part goes up. Yeah, so just as some road signs, if you will. So let's say we define Ts as the serial time to conduct all the operations, and Tp as the parallel time to do the computations. And now we make a critical assumption, which is not a good assumption, but which we have to make, because otherwise we would have to stop here. Namely, the problem is that the communication time is difficult to estimate in general. So in simple analysis like the one we are looking at, we will simply neglect this. However, this does not mean that in reality this is a negligible thing. So in reality, communication time can be very significant, but in an ideal world, communication does not exist. Okay, so this is, I said something strange here, yeah? So in an ideal world, communication does not take any time, say this. So we need communication. But in reality, the time for communication can, of course, be significant, or very significant, actually. So this means our serial compute time, which we have just said above here, Ts, is equal to the time that we need to do the parallel work plus the time that we need for the serial work. And the parallel compute time is the time that we need for the serial work plus the time that we need for the parallel work divided by the number of workers. Yeah? N is number workers. Okay, so far not very difficult, I hope. So now we are interested in how much quicker, so in answering our question, how much quicker can we solve the same problem in a parallel process that we previously tried to solve in a serial process. And this, this quantity we call speed up. And speed up, unfortunately, is also called S. And because it's also called S, like the serial time, I will identify it by putting some serifs on it. Yeah? So this is now a large S. So the speed up, and we are interested in the speed up on the strong scaling. And what I've forgotten now to write here is that this is called the Amdahl's law. Amdahl's law. Okay, so this speed up S is simply the time for the serial execution divided by the time for the parallel execution. Yeah, so see this when you parallelize, obviously you get faster, so your speed up would be larger than 1, right? So this is what you assume. So now we can simply put the numbers here. This is S plus P divided by S plus P divided by N, so it's relatively simple. And what is then customary is to introduce two more quantities, namely the serial fraction. So this is the part of this, that is the serial, or not the part of this. The part of the work to be done that is serial, yeah, is the amount, the serial time divided by the serial time plus the parallel time. So this is the total time, so just the serial time divided by the total time. This is what we call the serial fraction. And then there's, of course, a parallel fraction. Fp is then the parallel part divided by the serial part plus the parallel part. So this is the parallel part by the total part. Yeah. And when I say total part, you see here there we neglect the communication part. Yeah. So communication is not part of this model. So please.
So in this S, not the speed up,
The small s, yeah.
It doesn't include communication. It's just like the word for.
Yes, yes, it does not, because it is the case that we assume for the case that you run everything in serial. Yeah.
Okay.
Yeah. So. So in principle, so this of course also includes I/O, yeah, but it does not include any work that you have to do in addition just because you parallelize things.
Okay.
Yeah, like for example, you parallelize work over, say, these two workstations. Yeah, then in addition to the actual work that you have to do is you have to send data, put it in buffers, and read it from buffers, right? So this would be work that is only due to communication between the two workers, yeah, and not, yeah. So, and this is not included here. So we assume that all the workers have equal possibilities to access all data resources, so that they don't stand in each other's way, so to speak, yeah.
Okay.
So this here is called the parallel part. And of course, I mean, this is an idealized model, yeah. So now you can put these definition in the speed up definition, and you end up with 1 over fs plus fp divided by n, and this is rewritten as n divided by n plus fs plus fp. So now what we are now looking for is what speed up we can maximally obtain if we take infinitely many compute nodes and still we completely ignore communication between them. So this is something that we obtain by taking this equation here and take the limit of the number of workers to infinity. And this is, of course, the limit of the number of workers to infinity of n divided by n f plus fp. And you can very easily see that when n gets large, yeah, both parts, denominator and nominator, both gets large, and the parallel part then becomes negligible, and we end up with 1 over fs. So, is this larger or smaller than 1? This fs, is this larger or smaller than 1? No, I mean, is this limit, the speed up, larger or smaller than 1? It's larger because fs, so fs is a part, yeah. Also, okay, maybe I should say fraction. So it's a fraction, so it's just a part of the program. So this is smaller than 1 and larger than 0. Oh, okay, hopefully it's larger than 0. And so it means it's always larger than 1. However, it is absolutely finite, right? So for a given program that has a serial fraction of fs, the speed up that you can obtain is finite. So you cannot go, even if you have infinite resources, you still need finite time. The speed up is limited by the serial fraction of the workload. So, and we have it that in strong scaling the speed up is smaller the speed up is always smaller than 1 over the fraction of the serial part. Okay, so this was strong scaling. If there is a strong scaling, then there's also a weak scaling. And this brings us to the second question, question number 2. So this different problem. How much more work can n cores do instead of 1. It's always annoying that I cannot touch my screen everywhere. So this takes us to this, what I just announced as weak scaling. And weak scaling is the problem size grows proportional I think it's called proportionally to the number of cores and the number of workers. So now instead of n bricklayers building 1 column, it is n bricklayers building n columns. Yeah? Something like this. Yeah, so you see this is a core, or no, we said this is worker. So one worker, one problem. And more workers, worker 1, worker 2. Yeah, they just get more problems to do. Okay, so here the serial time, is now, so if you take now the same problem, always the same amount of work, say, that you want to grow and give it to just one worker. Yeah, so the work that you do with many workers, if you ask the question, how much time would this need if we had only one worker, then this would be, of course, the serial time plus p times n. Yeah, the parallel time, the parallel part of one worker times n workers, right? And the parallel time would just be the serial time plus the parallel part of each worker. So now this is a little bit the other way around this to what we had before, where we asked the question, you have a given problem, and how much speed up do we get if we divide this between more people? And here's the other way around. We would have, say, a lot of work with a lot of workers, and if this work had to be done by just one worker, yeah, what would be the difference? And this is then given in Gustavson's law. So this is the speed up in under weak scaling. So here we have S, it's the same letter, speed up, S, is again the serial time divided by the parallel time. And this would now be S plus P n divided by S plus P. And also here we have again a serial fraction and a parallel fraction, which you can rewrite as Fs plus Fp times n. And now if I go to the next page and you go to the limit, I was at the limit of the page. n to infinity of this speed up is the same as the limit n to infinity Fs plus Fp n. And here now you can very easily see that this can give you an infinite speed up. So this will be a finite speed up, the wind outside, yeah? Even if it's hard to believe, okay. So in this weak scaling, so the strong scaling is actually limited. Yeah, so you cannot have infinite speed up, but in weak scaling you could actually have infinite speed up. Can be arbitrary high in principle. Okay, so this was what I wanted to say about strong scaling and weak scaling. So do you have any questions to this? Because we are now changing a little bit the topic in a minute.
Why is the serial part not scaled also?
Why is the serial part not scaled? Because the serial part cannot. This is the definition.
With one part is serial, and then we double the problem. Why is the serial part not doubled?
Why is the why is the serial part not doubled? Okay. This is the serial part. In the serial part actually doubles here because one worker does the serial. So you have more. Okay, how to explain? So your problem is
That in the formula Ts equals.
okay. So we are okay.
Why is it not n times s?
Yeah, the serial part. Okay. So it's the question: what is the serial part of a problem? The serial part of the problem is something that also is is something like general, like startup, something that you have to do only once, which actually defines it that it is not parallelizable. Like in the bricklayer thing, so you, for example, you have to mix the mortar. We had this example, yeah, and suppose you get enough. Suppose it does not matter. Okay, now you know you have to something else. So mixing mortar, you have more mortar, takes more time. But say you order your secretary orders mortar, yeah, and this also takes time, ordering mortar. But you can order this amount of mortar or that amount of mortar. Yeah. So there is always work that is not parallelizable because it has to be done once. Yeah. Okay. Is anything else? Then we come to another. Then we come to another topic, namely the roofline model. So now this gets us a little bit closer to the actual hardware and a little bit further away from this very, very, very theoretical thing. Still theoretical, but it also includes the interaction between your hardware and your software. Now I'm kind of making a table. On the left side, I will write hardware. So it's not really a table, but it's two columns. And on the other side, we have the software. And computation is, of course, always the interaction between hardware and software. And then also your performance of your program is dependent on what is the interaction between what hardware do you have and what software do you write, right? So the hardware, for example, is characterized by something that we call peak performance. Peak performance, this is, so this is P peak, call it P peak, and this is the maximum number of operations per time. This is time. So this comes in units. We call floating point flop. Yeah, flop is meaning floating point operation, and we are asking for floating point operation per time. So this is their unit of the performance of your processor. So how many floating point operations can your processor do in a given time per second? Yeah. So I mean, you read. So this computer has exaflops. Yeah. So unfortunately, this is then sometimes, not. This is then sometimes written as flops, without actually the what's this called? Without taking the fraction here. Yeah. So this is one part of your hardware, and another characteristic of your hardware is the bandwidth. Bandwidth. This is the maximal number, or the maximal amount of data that you can, maybe I should write amount of data, maximal amount of data transferred per time. and this comes in the units byte per second. So the peak performance is actually something related to your processor, and the bandwidth is something related to your bus. Yeah? And now you can ask, so which bus? You could have several buses, and then there could be, this is still a simplified model. Yeah. Also peak performance, what does peak performance mean? Does it mean double precision? Does it mean single precision? So what does it mean? Yeah. So you, of course, need to specify here. So in your software, what you have is also two things, namely O, which we say this is the number, not the number, the number. The number of floating point operations. So we make an assumption which is not completely true, that everything we are interested in is actually mathematic computation, so floating point operations. You have, of course, also other operations. And so there's the number of operations that you have to do, and then there is V, which is the amount of data that you have to move. So in here again, moving data means you have to read data from memory and you have to write data to memory. Both is movement. And depending on your hardware, these may not be the same speed. And that would be then a problem of your bandwidth. For example, reading data is sometimes cheaper than writing data. Yeah? This is, for example, on the GPU, the case where you can make use of constant memory, yeah, which can be read more easily depending on the hardware that you have. Yeah, more easily, can be faster to read just this memory than to actually write something. So you have to be careful what you mean by all of this. So, and then there is coming back to the software part, then there is something that we call computational intensity. So this is a feature of your program. This is what we call I here, and this is the ratio between the number of operations and the amount of data that you have to move. And therefore, it comes in units of floating point operations, flop, per byte. This is the computational intensity. Now, the question, and now this has nothing really to do with parallel programming, and we could ask this as question 3 for today, is how fast can one task on one processor actually be executed? So this we call performance P. And you see this performance has the same units as the peak performance. So you could always say, okay, we could use peak performance, but the reality is you do not reach peak performance. And now we ask the question, why don't we get peak performance, and why don't we get peak performance even theoretically we don't get peak performance? Please.
The data transferring from memory.
Yeah, also Is this the answer to the question? Or is,
I mean, why can be big performance? Was the
why we don't get peak performance?
yeah.
Okay, let's look at the lecture. Okay, I'm explaining you why we don't get peak performance. Yeah, in a minute.
I mean, I was answering that. No, we can continue.
Okay, let's, because we are close to it. So there is, of course, yeah. I mean, there is, of course, the two limiting. I mean, the simple answer is the world is not perfect, right? But let's assume a perfect world. Then even in a perfect world, there are limiting factors. And the limiting factor can be execution. Or, okay, let's say computation is better. Computation, and there, computation is limited by the peak performance. Again, I remind you, this comes in units flops by second. Then the second limiting factor is the data transfer. So in the data transfer can be computed from the computational intensity I times the bandwidth, and now this comes then in units, flops divided by byte times byte by sec divided by second. Now you see this computational intensity times the bandwidth is also a performance. Yeah? So it's of the same unit. And the performance that you can theoretically reach, this P what we call roof, so the maximally attainable performance, so this is not necessarily the one that you get, is the minimum between the peak performance, no, what am I writing? Sorry. P peak and peak performance and the computational intensity times the bandwidth. Yeah? So whichever is the first limit takes precedence, so to speak. Yeah? And this can be drawn in the so-called roofline in the roofline graph, which I tried to sketch like this. So what we have here is I, so this is the intensity. And here we have P, so performance. And what is important is this is a log plot. Okay? So because I'm now drawing it, it will not become very obvious, yeah? But the intensity is in logarithmic scale, and also the performance is in logarithmic scale in this. So now in this, we have here P peak. So P peak is independent of the intensity, right? So this is the upper limit here. And then we have a line I by Bs. So Bs, the bandwidth is a constant. If we multiply this by I, and then it's of course an increasing function with I, very obviously. Yeah, that should be a linear function. So this is a logarithmic scale. Why doesn't this look like a logarithm rather than a? It's just a. It is double logarithmic. So in a double logarithmic scale, yeah, you get a straight line for a straight line, right? So this is why this again is a straight line. Okay, then you see there is a switching. So this would go on here like this. But there is, if you will, a switching in the mode, and so we first have this increase here like this, and then it becomes completely horizontal. And this point here, this is sometimes referred as the knee. Okay. So this is how this plot looks like. So there's a few. Let me go to a next page here. Have you drawn this? Then I go to the next page. Okay. Few things. Do you need?
Sorry. What does that mean? Log plot.
This is a log plot. So you plot the intensity logarithmically and you plot the performance logarithmically.
Oh.
So like you see, this is this would be you the 1 over 2, or let's say put it this way. So this would be 1 over 8. So that the same distance would be 1 over 4, and then this would be 1 over 2, something like this. Yeah, so this is what we mean by logarithmic.
I didn't understand the syntax of the.
Yeah, so everybody clear what a log plot is? Yeah, okay. So where have we been? Yeah. So actually, what we want to do is we want to work at the knee. Because at the knee, so this is the point where these two lines meet, both the processor and the bus are optimally used. Now you can become very philosophically whether this is important for you or not, but the idea is a little bit like this. Computers are obviously general purpose machines. Yeah? So your computer has not been built for your problem, obviously. So they have to, when you build a computer, or somebody is building a computer, they have to make a decision how much to invest in the processor and how much to invest into the bus. Yeah? And you, if you want to buy a computer and you have some choices, you should also make a decision how much processor do I need and how much bus do I need. Yeah? Given my problem that I want to solve. So the thing is, if you are not, so at the knee, if you are at the knee, you're fully occupying your bus and you're fully occupying your processor. If you are right of the knee, you are fully occupying your processor, but you're not fully occupying your bus. If you are left of the knee, you are fully occupying your bus, but you are not fully occupying your processor. So this is therefore you should actually know this, because suppose your program works left of the knee, yeah, so in this region that we have here, in this region here, and you are not satisfied with your performance, it is not enough to kick out the processor and replace it by another processor using the same bus. Yeah? because your problem is limited by the bus and not by the processor. Yeah. So therefore, if you know this and you're always trying to solve the same problem, you can actually try to buy a machine that fits your problem. Or you can try to adjust your problem to your machine. This is what we are usually doing, because in reality, we just have a given machine. Yeah? Okay, so, genau. Of course, this is again all theoretically. This roofline is of course the optimistic. So the reality is always below the roofline. It's the optimistic limit of computation. So you could say this is actually the light speed. So you cannot go above the roof line, or if you go above the roof line, you have not calculated your roof line correctly. Sometimes you see points that go above one roof line, but then they are not quite done correctly. Okay, coming to an example to trying to understand this. Let's look at this one. Example. So, okay, I write a little bit of pseudocode, which is similar to C. Say we have double, and you remember double is 8 bytes. 8 bytes. So say a variable s is equal to 0, probably 0 dot, and we have an array A. And now we are doing a for loop for integer I is equal to 0. I is supposed to be smaller than n, so this is supposed to be an n. And I plus plus. And what we do is we calculate s is equal to s plus ai times ai. So one thing that is kind of a little bit annoying in C++ is that there is no easy, that if you want to take something to the square, you actually have to write it like this, because there is no easy way of writing a square function. There is a way, but it's a little bit inefficient. Okay, so this is the task you're supposed to do. And in order to calculate your performance, what you have to do is you need to know your computational intensity. So the computational intensity depends on the number of operations. So how many operations do we have in this loop? Okay, so are we sure we have n operations? So which one do you mean? Which is the operation?
The one which is in the fourth.
Yeah, so, okay. The one that is in, but, okay. Is it the plus? Is it the times? Is it the indexing?
Yeah, that is also an operation.
Yeah, but it's not a floating point operation. So this is another problem, you see. Because we have the indexing, we have another problem, yeah, because we have operations that don't count here, because we are just counting floating point operations. Yeah? This is why we will not reach the roof line actually, yeah? Because we are optimistic. There's additional work to do. Yeah? You could also say, okay, we are counting up I. This is also an operation. It is not a floating point operation, it's an integer operation. So we don't count it. So, but what do we count? Equal? Okay, so what is, we count equal but not in the operations. What is an operation? Yeah, like one we have an addition here and we have a multiplication here, right? So I would say these are two operations that we do n times. Okay? So I would count 2 n operations. So with regards to the equal sign, so what does the equal sign do? The equal sign stores data. But what we are, okay, so the other thing that we need is the number of bytes moved, right? The traffic. So how many bytes do we move here? And this is a little bit tricky. So moving data means reading data and writing data. So start with reading. What do we read? The first. Okay, we read A. Now it depends on how your computer is actually built. Yeah? We read A here and we read A there. Does this mean we read it twice? In principle, yes. On a modern computer, we will read it only once. So there will be some cache in between here, right? So or actually furthermore, or like this. Once you read it in a processor, it will end up in a register. So it does not need to read it again, unless your compiler is stupid. Maybe your compiler is stupid. It could be that your compiler is stupid. Then it will read it from the cache. But if your compiler is clever, it will put it in a register and just does it in a register. Now, you already see a problem here. It depends on your compiler, and you don't actually know what your compiler is doing. Right? Okay, but suppose your compiler is clever. What you're doing is you read it once. Yeah? So what is with the S? Do you need to read the S once? Or how many times do you need to read the S?
Once.
Yes, because S is a scalar, and it will remain in the register. Yeah? So you are not moving it around. So the thing that you are moving around is here the A, and this means that what you are moving is 1 times 8 bytes. Yeah, so the thing you are moving is a double. It has 8 bytes, so you move once 8 bytes. And S is not moved, or it's at least moved only once, which we neglect, as it can be kept in a register. But this, of course, is a question of both how clever your compiler is and how clever your machine is. But your machine would usually nowadays be clever enough to do this. So only AI is read. So, okay, since this was a problem, I will say this, I will write this here, that this here is an operation, and this also is an operation. So these are the two floating point operations. Okay, so I've forgotten something. This is of course n times 1 times 8 bytes, yeah, because we have to do this n times, yes. So this means our computational intensity, so this is I of this loop is 2n, I've written this small, 2n flop divided by 8n bytes. So you see we can cancel the n and we end up in 1/4 flop per byte. And suppose we have a machine given as with a peak performance, say, of 4 gigaflop per second, and we have a bandwidth of 10 gigabytes per second, yeah, then the picture would, now I have to draw this. This will certainly look extremely painful. Okay, say this is this here. So what we have, so this is the knee. This is what we call the knee. What we now have to compute is the intensity of the knee. And the intensity of the knee is the peak divided by bandwidth, yeah? Because this is the place. Let me briefly. Okay, I guess if you go back to this picture, I've forgotten to write this here. So the knee is where we get P peak is equal to intensity times bandwidth. Yeah, this is the definition of the. This is where these two things meet. These two lines meet, right? So okay. Sorry for forgetting this to write this. So this means that P peak is equal to intensity at the knee times the bandwidth. So we can take this as the intensity here is P peak by the bandwidth, and this we would get as 4 by 10, so 0.4 flop per byte. And that would mean we would be here at 0.4. And now, since what we computed is 0.25, the performance that we have, so we would have 0.25, and this will be close to this line because we are in a double logarithmic scale. Yeah, so it will be something like here, and this here would be the performance. So the performance that you would could reach, would now be lower than the peak performance. So you are limited by the combination. So this loop will be limited by the bus and not by the processor. So in here actually we can get at this point, yeah, we can get the theoretical performance that our loop could have. Namely, this is the intensity of the loop times the bandwidth. And this will be 1/4 flop per byte times, now we have 10 gigabytes per second, and this goes to 2.5 gigabytes per second. Yeah? So you see, we could have the machine would give you 4 okay, I saw your face, and you're right. So it's 4 gigaflop per second, of course. Yeah. So this is the performance that you could maximally get out of this loop. Yeah. Your machine could give you 4 gigaflops, and the you remember you will be on YouTube later. Yeah.
Is this PP and BS given, or
Is it-
is it given? Like
Yes. Okay. So you buy a machine. So this is the number that they will always give you. Yeah. So by our machine we have a bus. This is our bus width, our bandwidth of our bus. Yeah. So you go on in the internet. You look for a machine. They will tell you this is the number. We have this peak performance and we have this bandwidth.
also the knee calculation is not like subtract is dividing. That's it.
This is dividing. But what did I say? Subtracting. You see, we are at the knee when the intensity times the bandwidth is equal to the peak performance. Then this is the knee. Yeah. So we just divide by the bandwidth. We divide the peak performance by the bandwidth, and we get the intensity at the knee.
Oh,
Yeah. Very simple. So these are very simple equations here. Yeah. So we get 15 minutes left. And we do a little bit of, I would say, exercise kind of stuff. Namely, we look at other loops. Other loops. Okay, let's look at, for example, this loop here. So we have double A. Now we have 2 of them. Double A and B, and say we have a loop for the integer I equal to 0, I is smaller than n, and I plus plus. So we end up here as, and the operation that we do is AI is equal to AI times BI. So, question, number of operations. So, number of operations O. How many operations do we have? N. So, we have N flops, N flop. So, we have bytes transferred. This is what we call V. So how many bytes do we transfer here? 60, no. 2n. So now what are you counting? Which are you counting? It's 3n. So why? Okay, but it's also okay. Also, you have to take into account that it's double.
Oh, yeah.
So it is 3. So why is it 3? Because we read A, we read B, and then we write A. Yeah? So it's 3n, 3n times 8 bytes. So then this gives us an intensity of n flop per 24 n byte gives you 1/24th flop per byte. So this is the intensity here, and from this intensity you can actually compute what performance you could theoretically reach, which you can take as your homework. So another example. Another example would be that here for int I is equal to 0, I is smaller than n, and I and we do the computation s is equal to s. Where did I? No. Sorry. I is equal to AI BI times S. Okay, simple example. O is equal to how many operations? 2n. How much traffic? 3. 3 times 8 byte, okay, and times n, I forgot, and then the computational intensity is 1/12 flop over byte. Okay, and we use the last one where we now use float. Float s is equal to 0, array A, and say this is 4 int I is equal to 0, I is smaller than n, and we do I plus plus brackets. So S is equal to S plus AI. So this is again simple. It's probably a little bit too close to the one that we already had. Is O is how many? It's 2n flops. We is 1. Okay, so how many are read? Right, so I've already written it down. So you read it only once, yeah? Because you store it in S, which is in a register. She's in a register, and now the only difference is we have now 4 bytes, because it's a float, and this times n. So the computational intensity will now be 1/2 flop per byte. So if you do the same operations with different with a different data structure, you end up with a different computational intensity. So now, however, this is of course everything here is in an idealization. You know, I don't understand what you are saying, but I cannot guarantee. No, I cannot. I just want to inform you. I cannot guarantee that the people who later listen to it, because it's recorded, don't understand. Maybe it's a good thing that the Chinese explanation is somewhere in between. Yeah. So the idealizations that we do here is, for example, that the number of operations are known. Yeah? So this is a much bigger assumption than you may think. So we also assume that all operations have the same expense, so that multiplication is as expensive than an addition, this may still be true. We also assume that operations do not interfere with each other. So, for example, modern processors may be able to do several operations at the same time, provided the resources in the processors are currently available. Yeah, so then if they are available or not available, they could interfere with each other. And this is so this is one assumption, and we also assume that we know what actually causes memory traffic. I think this is something that is really difficult to figure out in reality. Okay, some cautions here. So the exact number of operations generated by the compiler is very difficult to know, because you are not writing your program in machine code. You let your compiler do the machine code. And the only thing that counts as an operation is determined by the machine code, not by your code. So then this is difficult, especially to count. Some tools can actually count it or measure it. I mean, I'm not saying that it's impossible. I just want to say that it may not be as trivial as you think. Yeah, we just count them and that's it, right? So, for example, which usually is a good thing, is that compilers may be able to merge operations. This is in particular the case with when you have a summation and a multiplication both together. Then it may be possible that your compiler does this in one step, or that actually the processor does it in one step, and the compiler translates it to an operation that is in this one step. So what is very difficult to know is what is actually in your cache and what is in a register, and what is in faraway memory. This is very difficult to figure out. I mean, I say very difficult, it's possible, but not necessarily trivial. Register in caches. And yeah. Okay. In order to go to a little bit more realistic picture of all of this, just a little bit more realistic picture could be like this. So there's the intensity, there is the performance, and we had this roofline here. Say this would be the roofline for double precision, computation. Right? So you may want to write your code in single precision. So if you're in single precision, you can do more operations usually. So your processor has a double precision peak performance, and it has a single precision peak performance. So this here could be the single precision peak performance, which is higher. And then modern computers also have something that's called the vector unit. And this would be the vector this would be the peak performance for vector operations, which is even higher. So, okay, so you have different layers of actually peak performance. And also on the other line, you would have a bus. This would be the bus to the general memory of your machine. And then in addition to the general memory, you also have caches. And say you would, for example, have an L3 cache here, and then you would have other caches like an L2 cache. So if your operations are in the cache, you can actually go beyond this line with your performance, because you do not need to load the data from the main memory, but you can read it from the cache, which is faster. So this here would, for example, be the L2 cache, and then there would, of course, be an L1 cache also. Okie dokie. Okay. Maybe I take a little bit more time, and then we take this away from the exercise, or would it be a problem? No. Okay. I finish off this chapter here. So say we should, right, so this is something that we should still do. Say this is our performance, and this is our intensity, and this was supposed to be this is supposed to be a horizontal line, I guess. So, and then you could have here one cache, so I'm simplifying again. This here is the bus, and this here is the cache. So I'm about to say this is a cache line. This is the line indicating the cache. It's not what we mean by a cache line normally. So now let me put something like this. So this part here is, if you are in this region, you are this was wrong. How do I get to the right one? So this is the compute. When you are here, you are compute limited. Okay, I was very inaccurate here. I should do this again. Say, which one was it? Like, okay, so in this, sorry. Which one was the right one? So in this region, right? In this region, you are compute limited. So now, in that region, we are bandwidth limited. Bandwidth limited, and then we could also identify, so this is an addition that is usually not used. Is it actually visible, or should I use orange, I guess. I should use orange. There. What is it? On the wrong. Ah! Maybe I'm too stupid for this computer. So this here, if you're in this region, you are limited. Yeah. So this is, then you are cache limited. So what do these things mean, and what should you do if you are in one of these cases? So if you are bandwidth limited, it means that arithmetic compute power in cache they are not fully used. So is this a problem? I don't know. You bought a too expensive computer for your problem, apparently. So if this is the case, I mean, you could choose a different computer, which is usually not that much of an option if you want to optimize your code. One step that you should think about is, if you are bandwidth limited, to better utilize your cache. Do anything that helps you utilizing your cache will increase the performance of your program. So, utilizing your cache is usually done by trying to do reading and writing more locally. So there are different techniques to do this. So for example, you want to process your data in a specific order that keeps more of them together in memory, in cache. Yeah, this will then improve your cache performance. So you will no longer be limited by the bandwidth, but potentially by the cache then, right? Or then potentially also by the performance, by the P performance. So if you are cache limited, so if you improved your code such that the bandwidth of your bus does no longer hinders you to go on, now you are utilizing the cache but not the arithmetic. I'm trying to do an H and an M at the same time. That's a typical dyslexic problem. So cache is utilized, but arithmetic compute power is not. So your processor is starving of data. So this, what you could do here then is completely in general, try to reduce reading and writing events. So you really have to dig into your code and have to ask you, do I have to read this data? Do I have to write this? Or can I somehow merge something, so that I don't need these events? So, and this, if you do this, you read less and the intensity is the operations divided by the operations. What you're doing is you move the intensity I to the right. Yeah? So if you are in this picture here, if you are in this picture and you are in this place here, so what you can do in order to get, or you would, for example, be in this place, yeah? So you are locked in here by the cache. If you reduce the number of reading events or writing events, the I is moving to the right, and then you can actually go up here till you come to the compute power. Yeah? So you can move the I, the intensity, and when you are compute limited, then you are using your compute, your processor, which is a good thing. But you're not using your cache or bus. This is not fully used. So now if you want to optimize your code, what you try is to simplify your operations. So you want to reduce the number of floating point numbers. This means if you reduce the number of floating point operations, the computational intensity is floating point operations per traffic. You reduce the number of floating point operations, you move the I to the left. Yeah? So this is I moves. Okay, it's not I move to the left, but I moves to the left. Yeah, and remember you want to occupy you try to occupy your computers as good as possible. So one thing that you can do here is, if possible, so this is a relatively complicated thing, if possible, make use of vector operations. Okay, so I have a few more points that I just want to mention, yeah, to get this across before we go into the break. So, you know, if you want to optimize your code, you need to know what you are doing, yeah, and sometimes you will be surprised that you do everything you can and nothing happens. Yeah. So, for example, if you are in a bandwidth limited, if your problem is bandwidth limited, and you say it's slow, how do I get it faster? And you think, okay, let's simplify my operations, and you see nothing happens. So in bandwidth limited computation, simplifying operations does not help you anything, as long as you're dealing with the same data. So this is an important question in if you are concerned with you have a relatively complicated equation and you could say, do I want to simplify my complicated equation with a simpler equation? Yeah, then you would have to look up whether your problem is bandwidth limited or compute limited. If it's bandwidth limited, using a simpler equation will not change anything. Yeah, because how many operations you do on the same data does not matter. Yeah, because your processor has free space, but your bandwidth is already saturated. Yeah, so this will not help you if you try to optimize bandwidth limited code with reducing the number of operations. The same in reverse is if you are in a compute limited computation, you have actually free bandwidth reducing read and write events does not, or I should say probably may a little bit, but not really, increase performance. Okay, and therefore what we are trying to do, and I will finish off with this, what we call a well-balanced combination of hardware and software always works at the knee. As closely to the knee as possible. Okay, sorry for taking over time. We'll have now a break. Let me